This video explains how to integrate the Clausius-Clapeyron equation using indefinite limits and the applications of that expression. In prior videos, we have seen both the differential form of the Clausius-Clapeyron equation and the integrated form using finite limits. These two expressions are related to the phase diagrams that we have been seeing earlier on. Specifically, they are related to the phase boundaries of the phase diagrams that involve the gas. Okay, so there are two such lines, which are the liquid to gas phase boundary and the solid to gas phase boundary. The differential form of the Clausius-Clapeyron equation allows you to calculate what the slope of these two lines is at any point in the diagram. And the integrated form of the Clausius-Clapeyron equation allows you to, if you know any point in this line or that line, you can actually predict what another point in that line would be at higher pressures or lower pressures. Okay, so those are the two applications of the expression that we have seen until now. Okay, notice that in order to use the integrated Clausius-Clapeyron equation as we have seen it, you actually need to know what the enthalpy of the phase transition is. The question that we ask right now is whether maybe you actually know two boiling points right here, TV and TV prime, and the two vapor pressures, or the pressures at which those boiling points are. This is P1 and P2. Okay, we can call this T1 and T2 to make here contact with the integrated Clausius-Clapeyron equation. But if you know these four parameters right here, then in principle you can actually solve for the enthalpy of that phase transition. In this case, it would be evaporization. So that seems to be a pretty useful thing to do because, again, these enthalpies are important quantities. They participate in a variety of calculations in thermodynamics, how many energy you need to supply in order to be able to make that phase transition, what is the change in entropy in that phase transition, and so forth. All right, so the question is, can we actually do that, or is there a better method to calculate that enthalpy of vaporization from the phase diagram? Well, notice that in principle you can actually do that directly, but you would be missing on a lot of information. For example, suppose that you actually have not only 2 points, but you might be able to have maybe 10 points in this phase boundary. The question is, how you actually involve those 10 points that you have right there to calculate a much accurate value of the enthalpy of vaporization than you can get when you only are using 2 points. Okay? When you're only using 2 points, if you have a slight error in one of them, like this, it turns out that if you're only using that point and this point through that equation to calculate the enthalpy of vaporization, then that enthalpy of vaporization would be prone to large error. However, if you're involving 10 points, then the statistical significance of that enthalpy of vaporization is going to be much greater. Okay, so again, we'd like to devise a way to actually be able to utilize data of vapor pressures as a function of temperature more than 2 points to be able to calculate an accurate enthalpy of vaporization for the phase transition. Okay, so how do we do that? Well, the way to do that is to actually repeat the integration of this expression, but instead of using limits in the integral, we can actually carry out the integral without limits. Okay, so we reset the integral right here. That is going to be differential of P over P equal to the enthalpy of that phase transition divided over R, and then we have differential of T over T squared. Okay? And the way that we have integrated this before is by using here limits in the integral. Okay? But what we can try now is to actually see if we can do this without any integration limits. The way to do this is as follows. The integral of differential of P over P is simply natural log of P plus a constant. Okay, that's the only difference between having limits or no limits in the integral. Okay, and the integral of that expression is going to be equal to delta H of the phase transition over R, and then that is going to be equal to minus 1 over T plus another constant. Okay, which might be different or it might be the same. Now we can consolidate those constants. So the first thing that I'm going to do is just change the sign here and make that be a plus, which means that this goes away. And then I have an expression that is going to look like natural log of P is equal to minus delta H m alpha to s over r 1 over t plus constant 2 prime, which will just be this constant minus that constant. Alright, so this is the final expression of my integrated Clausius-Clapeyron equation when with indefinite limits, when you don't have when you don't use limits in the integral. The question is, how good is this? Again, remember that the goal of this process here is to be able to determine an enthalpy of vaporization that is accurate and that you can compute by involving many points in the phase boundary. Okay, so again, the idea is that you're going to have a phase boundary like this, P, T, this is your phase diagram, and let's concentrate here in the liquid to gas phase boundary, that one. And that means that you're going to have various vapor pressures as a function of the temperature. Okay, so you're going to have here 1 point, 2 points, 3 points, 4 points, maybe 10 points. Right, so the question is, how do you involve all of those to be able to compute the vaporization enthalpy in this case? Well, if you actually take a look at it, notice that here, this is what you're measuring, or this is what the data that you have, the vapor pressure, and then you also have the temperatures. Okay, so if you actually stop to think about this is the representation of a straight line if you plot this as natural log of P versus 1 over T. All right, the way that that is going to look like is like this. Natural log of P versus 1 over T. According to this expression, this should be just a straight line in which the slope is going to be this, okay, and the intercept with the axis is going to be that constant. Okay, so here you will have your 4 or 10 points, however many you've been able to get out of the phase diagram, and you can trace that straight line, and the slope of that line is equal to the minus enthalpy of vaporization, in this case of that substance, over the R constant. Okay, so this seems like a nifty method to calculate vaporization enthalpies for phase transitions from the phase boundary. Okay, something that we have to keep in mind is that, again, these values tends to change a little bit with temperature. Okay, so the value that we get out of this fit would be something that is reasonably good for the interval of temperatures over which you're trying to do this calculation, but not much further below. Okay, that's kind of a limitation of this technique, which otherwise allows you to calculate a reasonable enthalpy of phase transition from the Clausius-Clapeyron equation.